Hi everyone, my name is Yulia and thank you for tuning in today. This is CS50 week 3 sections and today we're talking about algorithms. As I said, my name is Yulia and I'm a preceptor here on campus at Harvard, and today I'm going to walk you through the following things. So on the menu today is searching, sorting. We're going to talk about different algorithms, their runtime. We're going to also try to figure out the algorithm from the runtime ourselves. We're gonna touch on structs and do an exercise there, and finally we're gonna talk about recursion and try to see some real-world examples there. So let's get started, and let's start with searching. So for example, in the lecture we were trying to look for the Monopoly money in those red lockers. Well, today let's consider a different example. Say I have these books. So I have these 7 books lying around on the table, and say I'm looking for a book called Journey. So one of the approaches to take is to just look at each book one by one. For example, I'm going to look at Odyssey first, and then it's not Journey, so I'm going to move over to the next one, which is Inferno. It's not Journey. I'll keep going. I see Macbeth. It's not Journey. And then finally, my 4th book is the one I was looking for. And so this algorithm is linear search, right? Where we just look at one element one by one, and we're trying to find the one we're looking for. Now let's consider binary search, and recall from the lecture that in order to use binary search, our list of objects has to be sorted. So I spent some time sorting my books, and this is what I ended up with. So I have all my 7 books sorted alphabetically, and again, in this case, I'm looking for a book called Journey. Well, how does binary search work? It is really sort of like divide in half and conquer, right? Divide and conquer, divide in half and conquer. So first what I'm going to do, I'm going to look in the middle. I'm going to look at the book called Inferno, right? It's the 4th book in the order, so the middle. I now see that it's not Journey. So then I start thinking, is Journey to the left or to the right, right? Is J before I or after? I know it is after, so now I'm going to focus on the right half. And again, I'm looking at the book in the middle, which is Macbeth. And then once again, it's not the book I'm looking for, it's not Journey. So then I'm going to ask the same question again. Is J before M or after M? It is before, so now I know that I need to look to the left of the current book that I'm on, and thus I see Journey once again. So we've considered 2 algorithms, right? Linear search and binary search. Now let's talk about how much time does it take us to complete each of these algorithms. So let's consider a table like this, where we have linear search and binary search, as well as the worst case and the best case scenarios, right? In worst case, how many times would it take us to find our book, right? Like say Journey was in the very, very end of our list. Well, in linear search, that would be 7, right? Because we need to look through every single book until we find the very last one. In binary search, it would be log 2 of 7 because we are dividing our problem in half every time. Well, let's scale it up a little bit. If I had n number of books, what would be my worst case scenario then? Well, it would be n, right? And the same way for linear search, we'll have n, and for binary search, it will be log 2 of n. Well, now let's introduce another layer to this analysis, and let's introduce a notation called big O, right? Again, we're like scaling up and we're saying approximately what is our like worst case scenario, like if the book is a very, very end, if we have n number of elements. Let's now consider the best case scenario, right? What could have happened if our book was the very first one, right? Like, for example, if I was looking for Odyssey that was in the very beginning, how many steps would it have taken me if it was the first one? Well, in linear search and in binary search, right, it would just be 1 step. So in linear search, if my book was the first one, it would just take me one step to find it. And in binary search, that would be the case sort of like where the book is in the middle. And again, let's scale it up and introduce another notation, which is called omega. So now we have worst case and best case scenarios, big O and omega notations for our linear search and binary search. Okay, so these tools would be really helpful as we're jumping into our next exercise talking about sorting, but also as you try to consider these theoretical levels in the concepts that we're talking about. And before we go to sorting, what questions do we have about searching or runtime analysis? Someone asked what happens if we don't have sorted arrays. That is actually a great question. So it is always a consideration that you should make yourself, right? When should I use linear search or when should I use binary search? Well, if the list is sorted, right? If all of your objects are in alphabetical order or in numerical order, binary search would be a better way to go, right? Because you can from the very beginning just have the problem in two. But what if you have like 500 items, right? And you're only searching it once. Well, consider the time that it would take to sort everything first and then do the binary search. So if you're trying to look for something just once, linear search might be the way to go. But if you know that if you want to look for something repeatedly, you might consider sorting it first, right? To give yourself this perfect orderly list and then using binary search to find the element you're looking for. Yeah, someone asked about going over the C code. We'll definitely go through one of the examples later on when we're talking about structs. Okay, someone asked, can we use binary search for odd numbers? Again, you can use binary search sort of like on any list as long as it is sorted, right? Because it kind of like anchors on the idea that we go to the middle and then we try to see if the value or the book or the number that we're looking for is less or bigger, is smaller or bigger than the one we're currently looking at. All right, let's keep moving, and now let's talk about sorting, right? So we've seen a couple of different algorithms in lecture, and here's some of them alongside the big O and the omega notation. So in the lecture, we saw merge sort, which is again our like divide and conquer approach, where we cut the problem into small pieces and then merge them back up together recursively. Selection sort is where we remember the smallest number we're looking for and then move it to the very beginning of our list. And bubble sort, you can even infer from the name a little bit, we bubble our highest number to the top, right? It just like goes up to the top if we even counted it by swapping the elements every time you look at them. And here are their big O's and omega notations. So again, you can see from our sort of like theoretical definitions that merge sort does perform faster than the other two, since selection sort and bubble sort have big O of n squared. But now if we look at the third column, which is omega, we can notice that bubble sort does actually perform better than the merge sort in the best case scenario. What sort of like best case scenario can happen here where bubble sort can perform better than merge sort? In which case would we use bubble sort over merge sort? Exactly, if the list is already sorted, right? If we want to do just one pass to figure out if the list is already sorted or not, bubble sort might be a way to go. Well, let's actually see an example of these sorting algorithms and the runtime. So let's consider this. We have 3 different algorithms called sort 1, sort 2, and sort 3, as well as different text files with the numbers of either reversed, sorted, or random order. And our goal today is to figure out which algorithm is which. The trick is that we can't actually see the code. And if I go to my cs50.dev now, and let me open one of these files. So let's see. Let's open sort 2, right? This is not code. I don't see what it is because it's already compiled. So this is the trick today, right? We're going to do some testing and figure out which algorithm is which by looking at the time that it takes each algorithm to sort different numbers. All right, so let's get started. And at first, let's examine what kind of files we have here, right? What is going on? So let me close this tab and let me open answers.txt. So this is the file where we're going to write down our final conclusions. So as I said, what we want to know is what kind of algorithm is each of these like sort programs are. So sort 1, sort 2, and sort 3. And how do we know that, right? And I already gave a little hint of how we can figure it out, but does anyone want to type in the chat exactly sort of like what approach we might want to take here? How can we figure out which sort is which if we can't see the code itself? Any suggestions of how we would like to proceed here? Yeah, so we could use timing. Okay, perfect. And so let me show again what files we have here. So as you can see, we have different kind of files in our folder already. So random, reverse, or sorted, different number of elements in each list. What two variations should we use here, right? Again, considering like the best case and the worst case scenario. What would be our worst case and best case scenarios here in terms of text files we want to use? Any ideas? Okay. Yeah, so someone said worst case would be longer time and best case less time. Exactly. And then someone said we can use reverse and sorted, right? So that's exactly what I was looking for. So the sorted one would give us the best case scenario, right? So for example, if we go back to our slide, the sorted one is where bubble sort would perform the best because it has just omega of n, and it would be the fastest algorithm here. And then if we're looking at the unsorted one, right, we can also have some expectations. So for example, unsorted one, in the reverse order is the worst case scenario. So we can expect merge sort to perform a little better than the other two. But let's go back to cs50.dev and actually let's try to run these experiments, right? And if you go to the page of this problem set, you can find more specification, but I already know that to time these algorithms, I can type the following command. So time running the algorithm that I want to test. Let's start with sort 1, and then specifying the file that I want to run it on. And so let's start with the worst case scenario, which is reversed 50,000.txt. And so we'll take some time to think and try to sort this list. But here on the bottom, what I see is the time, right? So you see a couple of different ones, but the one that we want to look at is the real time, right? It's sort of like the stopwatch, the timer on your phone that you have. So let's take notes. So we know that on reversed list, sort 1 took 5 seconds, right? What about the sorted one, right? Like we said, this would be our best case scenario. Let's try timing that one too. So once again, I'm going to use time sort 1, and in this case, sorted 50,000 txt. And this one was much quicker, right? So we definitely see that that's the best case scenario. And let's just take a note of that. So on the sorted list now, sort 1 took 0.3 seconds. Okay. Let's keep going. I think we can make some guesses, but let's just try one more algorithm so we can have some comparisons to do. So I'm going to do something very similar where I'm just going to time sort 2 on the reversed list, 50,000 txt. Okay, so that was also very fast. On the reversed list, sort 2 took 0.275 seconds. And now let's do the same exercise just for a different list. So sorted 50,000.txt. This one was also really quick. Okay, so let me take a note, and in a second we can chat what is going on here. So already we can sort of like take a few guesses, and let's go back to our runtime analysis chart right here. So as we talked before, merge sort would perform in the same way on both the worst case and the best case scenario. So if we go back here, which sort so far is performing similarly on both lists? Sorted or unsorted? Sort 2, exactly. And we see that there is some tiny differences. Like for example, on the sorted list, it took 0.3 seconds less. We should also consider different systems and operations running in the background, but roughly it performed in the same way, right? So maybe we can type something, maybe merge sort. Okay. And how about sort 1? What guess can we make here, right? It took 5 seconds on the reversed list, but much quicker on the sorted list. And going back to our diagram here, what do we think is sort 1? Exactly, so it is bubble sort. And maybe let's type bubble sort, and maybe we'll be proven wrong in the very end. But to make final conclusions, let's run the same timing operation on sort 3. So I'm going to do time sort 3 on the reversed list, reversed 50,000 txt. Oh, sorry, that was sort 2. Let's do this again. Let's run sort 3 on the reversed list, and it's thinking. Okay, so on the reversed list, sort 3 took 2.4 seconds. And what about the sorted list? So we can do time sort 3 sorted 50,000. It is thinking again. So on the sorted list, it took 2.1 seconds. And let's go back to our diagram again. So let's make our final guess. What would be sort 3? Selection sort, exactly. So as we can see from testing on different lists, right, and coming up with theories, it actually, even like in the real time, we can guess which sorting algorithm is which. And to sum it up again, bubble sort performed way better on the sorted list, but took a while on the reversed list, right? So we can conclude that the omega notation for the sorting algorithm is smaller than the big O. So this would be bubble sort. Merge sort, or sorting algorithm 2, performed the same on both lists. So again, thinking back to our diagram, that would be merge sort. And then sort 3 sort of took similar time on both lists, which would be selection sort, right? So feel free to play around with it more on your own. There are a few different files you can check out. It's good to take down notes and try to compare the times. We don't really care about these like small differences, like 0.2 seconds, but seeing the bigger picture and understanding how much time an algorithm took, we can sort of like deduce which one is which. But before we move forward talking about structs, what questions do we have about searching or sorting or the runtime analysis? Okay, let's see. Someone says, why did bubble sort take longer than selection sort? Again, as I said, it sort of like depends on what is going on in the background, right? So that is also a consideration to make. Again, it's just like a few seconds that the difference is, but sort of like seeing, again, the bigger picture and especially comparing how much time it took on both the reverse and the sorted lists. Okay. Any other questions? I see that people are also responding to each other's messages in the chat. That is great. We love helping each other. Yeah, so someone asked the difference between method and function. We will talk more about that when we get to Python, because as you mentioned correctly, that's object-oriented programming. Someone says, why is merge sort more efficient than bubble or selection sort? So remember from the lecture, merge sort tackles things recursively, right? It divides the problem into smaller pieces and then tackles the small bits first before coming back all together. And you can see a bunch of different visualizations online actually of how it actually is happening, but because it sort of like tackles the problem small bite at a time, it just ends up being so much faster than bubble or selection sort. It sort of like works with the entire list every time it traverses it. All right, for the sake of time, let's keep moving. And now let's go to structs. So again, we're taking another step up in our syntax and our data structure. So last week we talked about arrays and strings, and today we're adding on another layer to that. Let's consider elections, which is a hot topic here where I am right now. And this is actually what the problem set 3 is also about, elections. And let's consider how we might want to tackle it and how we might want to store information. So let's consider this new syntax, where on this slide, we're defining a new data structure called candidate. And the way that we do that is the following. So at first we're gonna define a type, right? So the structs or the custom data structures that you're creating are certain types in C. And because no one before created this type candidate, it is on us to define it properly. So the first step in our syntax is type def, then followed by specifying there's gonna be a struct which sort of like combines a few pieces of information together. And we're gonna call this struct candidate. So again, the first line, type def struct, is something that pertains to C syntax, and the last line, candidate, is just how I'm choosing to name my new data structure. What is going on inside the curly braces? Those are called attributes or members. And these are your specifications, right? Like the customized element to your data structure. In this case, I chose to use attributes name and votes because I wanted to record the name of my candidate and the number of votes they received in the election. Again, as before, it's very important to specify the type of that element. So in this case, I'm choosing string name and int votes, because votes are numbers, I'm going to record them as integers, and the name is text or string. Okay. How do we actually sort of create these new variables, right? So before on this slide, we saw, okay, we can define them and we have this new data structure. How do we use it? For example, if I wanted to create a new variable of type candidate, I could do it in this way by saying candidate president. I'm specifying the type candidate, right? It is no longer struct candidate, it is just candidate because it is the new type that I defined earlier in my code. The name of the variable is now president, right? So again, president could be any sort of word here. It can be candidate Yulia or candidate Carter, but candidate is the sort of like the more permanent word that we care about right now because it is the type of our new variable. And how do we actually access these elements, right? So right now you can sort of like imagine we created again this like box that is called president, some sort of like variable we're going to store something. How do we define our attributes? So let's consider this. For example, if our president's name is Alice, the way that we access those specific attributes is by using this dot notation. So by saying president.name, I can access the specific sort of like cell corresponding to the name attribute where I'm going to store name Alice. And then similar for votes. I'm going to access it by saying president.votes and putting 10 or any other number in here. Okay. Well, what happens if we had multiple candidates, right? In this case, I've only considered one situation when I have one president and one candidate, but what happens if I want to have multiple candidates? How can we solve that issue? What if I have multiple candidates? Array, right? So I want to use an array. But how, right? We have our struct candidate, this new data type that we created. Can I put it in the array? And in fact, I can. Recall from last week, I can create arrays of any kind of type that I want, including structs, right? Candidate is a perfectly legitimate data type that I now created in my code. So I can do something like this, where I have an array of 3 candidates, and I sort of have this 2D system going on, right? Where I have the name and the vote cell for each of my 3 candidates. Well, again, how do I access it? I know that I can access each of the attributes in my struct using a dot notation. But what happens when I have an array? Well, recall from last week that we just used the square brackets notation. So in the same way as before, if my array is called candidates, I can use the square bracket notation, specify 0, and in that way get the first element of my list, which is Alice and 2. Again, this will give you the entire struct that you're looking for. If I, in turn, want to get just the name, I use the dot notation. So again, going sort of like step by step from the bigger scale to the smaller one. My array is candidates, right? That is my bigger data structure that I'm looking at. If I want to grab the first element in my array, I use square bracket 0, which is giving me this specific struct in the array. And then if I want to grab the specific value, I'm sort of like taking another step into it using the dot name syntax to grab Alice's name in the array. Okay. There's a lot of different layers, so before we go into the exercise, I'm gonna pause and ask what questions do we have about structs and arrays, how do we access different elements? So someone asked, what is the main difference between struct and class? So class is something that you will see in Python, although we're not going to talk about it in this class, but structs is what we're using in C right now. Scrolling. Are there any questions? So someone said, how can we define the data type of the array? And we're actually going to see it in just a second. We're going to move over to test50.dev, and maybe this would be the perfect segue to our exercise. So let's consider this. Our goal is to create an array of 3 candidates in a very similar way that we just did visually. We're going to populate an array using users' input, something that is familiar to us for a few weeks now. And then we're going to combine our searching algorithm to find the most voted, to find the most votes awarded to any single candidate, and then print out that name. So let's move over to cft.dev. Let me close the sorting exercise. And let me now open our exercise with structs. So I took some time before our section and I already pre-typed some code, so let's quickly walk through it. In the very beginning, we have our headers. It is what allows us to get users' input, and the standard.io.h. We then define our candidate struct, right? Exact same syntax that we used on the slides just now. And then we're going into our main function where we're already defined variable num, which is the number of our candidates, as well as the array that will store our candidates. And then going back to the question in the chat, it is this is the syntax for defining the array of specific new customized struct or data structure. So again, as before, was it int or string or long, the syntax remains the same. You want to specify the type, which is candidate. You want to give your array a name, which is candidates. I know this might be a little bit confusing. Again, this part could be anything you want. And inside of the square brackets, I'm defining the size of my array. Again, I could have said something like square brackets 3, but recall from last week, we want to avoid using these magic numbers, right? If I just put 3 in here and then someone else looks over my code, they will have questions, right? Like, why is 3 in there? So that's why we want to define specific variables. Also, so that it's easier to change them later. What if I have more candidates and I want to change it to 6 later on? Okay, let's change this back to 3, and let's do the first step of our exercise. So what we want to do first is populate the array with users' input. Okay, and how do we want to do that? So if I have 3 candidates in my array, I could go one by one, but what would be a better way to populate the array? What would be a better way to populate the array with the names and the votes for all 3 people? Exactly, a for loop. So that's exactly what I'm going to do here. For int I equals 0, for I less than num, because I defined num before, again, I'm not using some magic numbers, and then I++, I'm going to populate my array. And this is where like the tricky syntax kicks in a little bit. Let's first write the functions that we're familiar with. So for example, getInt for votes is how I'm gonna get the votes for my candidates, and then getString for the name. All right. But where do we actually put, right, the user's input? Well, I know that I want to put it into the array, but I also want to access those specific cells for each candidate. So as we just saw on the slides before, what I'm going to do is I'm going to say candidates for my big array. For the ith candidate, in the name attribute, I'm going to store the name that the user gives me. And then again, in a very similar way for array candidates, for the ith candidate, in the votes attribute, I'm going to store the number of votes that my user is giving. Okay, so let's try to compile this to see if it runs. Okay, it compiles perfectly. Now let's try running it. So for example, name Yulia 5, name Carter 4, and then for example, Andrew 4 as well. Okay, we're not seeing anything printed out just yet. We're just compiling it and running it step by step to see if we get any mistakes, but let's keep moving. And now let's actually get to the interesting part, right? Like searching for the highest votes for a given candidate. Well, this would be a multi-step process, right? First, I want to find the highest number of votes, and then I want to print out that name. So one way to do that is first to find exactly what is the highest number of votes, right? For example, right now I can see it's 544, so just visually I know that 5 is the highest number. But again, recall the computer can't just access all the information at the same time. It has to go one by one, looking at every single element one at a time. So let's consider this. I'm going to create a variable called highest vote, where I'm going to record what would be the highest vote at every given time. And let's just start with 0. Then I'm going to, again, use a for loop to go through my array, looking specifically at the vote attribute and comparing to my variable highest vote right here to see indeed which vote, what is the highest number of votes that we have. So I'm going to make a for loop in a very similar way to what we've done before. And now I'm going to compare, right? So I'm going to use an if statement. And what I'm going to compare is if candidates, if the specific candidate, and then the votes field, right, the attribute, is it higher to the highest vote variable that I've recorded? Right? So for example, consider if we're going through the array that I populated right here, candidate's 0 votes would be 5, because I'm the first candidate and the number of votes is 5. So then the if statement would be something like, if is 5 greater than 0? Well, it is. So now I want to change 0 to 5, right? Because I always want to keep track what is the highest number of votes that I've seen so far. So I'm going to say highest votes now equals to the number of votes the specific candidate that I'm looking at has, right? And I'm going to keep going. For example, if the in the new array, the very last number of votes is maybe 8, I want to make sure that I record that number so that I know what I'm looking for later. Okay. So let's maybe print f votes, highest vote right here, so that we know we did everything successfully. Highest vote. Okay, let's try making this structs. Okay, and now let's try running it. So for example, Yulia 5, David 4, and then Carter 8. And then ideally, what number should I see in the end? We have 5, 4, and 8. What should my printf statement print? 8, exactly. So I press enter and I see 8 in the end indeed. So at least for now, we know that this part of the algorithm is working out fine. Okay. So now that we know, again, what would be the highest number of votes, we're going to print out the number of candidate that has that number of votes. Again, as humans, just by looking at the terminal right now, well, Carter has the highest number of votes, so he won the elections. But again, the computers can see everything in the bird's eye view, so we need to go one by one, comparing the number stored in the highest vote to the number of votes the current candidate has. So in a very similar fashion, once again, I'm going to make a for loop int I equals 0, I is less than num, I plus plus, and inside of the for loop, I'm going to use a very similar if statement where now I say, okay, I'm looking at the current candidate's number of votes, and if it is indeed equal to the highest vote that I recorded earlier, what I want to do is print out their name. Okay, candidates, I, name, semicolon. Okay, let's try compiling it. So make structs. Let's try running it. Yulia, for example, 4, David, 5, and Carter, 9. And indeed, now we see that Carter won the elections because he got 9 votes, right? So we approach this with some steps, right? We indeed had almost like 4 of them. First, creating the candidate struct, considering what kind of attributes do I want in my struct to be present. Then we used a for loop to populate the array with users' input, getting in those numbers and those votes. Next, we found the number of highest votes in the candidates, right? So you might consider this a step of elections has ended and we have all of this information and the number of votes each candidate has. So then we're gonna go look at each single number of votes, determining which one is the highest. And in the very end, we again go one by one, comparing the current candidate's number of votes to the highest number we've recorded before. And then if they're indeed equal, we will print out that candidate's name. Okay, I already see some questions coming in, so I'm gonna pause here and answer them, so feel free to type more. Yeah, so what is a struct really? Is it an array of variables or an array of arrays? It is sort of like a custom data structure that you are creating, right? So it is not an array per se, but you can sort of like imagine it as these like stacked cells that I was showing just now, right? It is different attributes, right, combined together. And as David mentioned in the lecture, structs are really helpful if you want to tie some information together, right? If I had a different array names or different array votes and I was trying to piece those two together, I might mismatch some of the information. But by using the structs, we sort of keep different pieces together so that we can use them later. Okay. Someone says, in comparing, can you use stir compare? Well, we were comparing the numbers, right? So just using 2 equal signs worked out perfectly fine. str compare is where you want to compare strings, right? In the string library. Alrighty, let's move forward and let's talk about our last topic of today, which is recursion. I know it usually tends to be the scariest topic because it just escalates so quickly, really because we let the computer do a lot of the parts himself or itself without us really controlling it. So let's consider this real world example. So some of you might be familiar with factorial, where it really is just the exclamation mark operator that expands to the following form. For example, factorial of 1 is 1, factorial of 2 is 1 times 2, factorial of 3 is 1 times 2 times 3. So the process is really take the number that is before the exclamation mark and then multiply it by the numbers, sort of like subtracting 1 every time until I reach the end. So now let's reverse it to helpfully visualize the process of writing the recursive function a little bit better. So I just flipped it a little bit and I'm starting with 4 now. So what is really going on behind it, right? I could expand factorial of 4 to 4 times factorial of 3. And then I could expand factorial of 3 as 3 times factorial of 2, and so forth and so on, right? This is where that recursive, like the recursion concept kicks in a little bit, Because I can just look at the first line where I have factorial of 4, and I was like, okay, I have the number 4, and then something else is going on, right? And I get that number back. So let's consider how we might want to write it in code, and we're not going to switch to code yet, but let's imagine that we have a function called f that calculates factorial of a number. And let's say I want to calculate a factorial of 4. This is how I would break it down. Again, you can just imagine I'm substituting exclamation marks with the function f. So in the beginning, I call factorial 4, right? I put in the computer 4 and I want to get the factorial of that number. But breaking it down, again, we can see that it really is just 4 times factorial of 3, which in turn is 3 times factorial of 2, etc., until we hit 0, right? In which case, factorial of 0 is 1, and with it we can stop, right? There cannot be factorial of a negative number. So if we expand it like that, how do we put it back together? Well, we can notice that the very bottom line is going to return 1, right? The factorial of 0 is 1, and then we're multiplying it by 1. So if we take the output of the very bottom line and sort of like plug it back up, we will get 2 times 1. In the same way, we have 2 times 1 equals 2, and so we can plug it in instead of f2, which in turn will give us 3 times 2. And we're going to make this step a couple more times. So 3 times 2 is 6. And so we're substituting f3 with 6. And now we have 4 times 6, which we're again plugging back up, and we get 24 in the very end, which is factorial of 4. Right? So we see that it's really just expanding it to the very end until we hit our base case, right? In which case I know that factorial of 0 is just 1. I need to return 1 in my program. There are no other factorial calls I can make. And after that, after I hit my base case, I collapse it again, right? I go bottom up, looking at the output of each line, combining it all together in the end. So let's go to our cs50.dev and let's try to code this together. So I'm going to close this tab and open factorial.c. So I already pre-wrote some code here, right? I defined my function f that we're going to use. In my main function, I'm getting user's input. Again, I want to ensure that I only get positive numbers. So we're going to the do while part that we also used in Mario earlier in this class. And then in the end, in the end of my main function, I'm calling the factorial function again on that number that the user gave me, and then I'm just going to print it out, okay? So let's actually define this factorial function using recursion. So again, I have my prototype here up top that I already pre-wrote. So this is what I'm going to start with. As I said, there is this base case, right? And then there is the recursive case. And let's go back to the slides for just a second, right? My base case here is 0, right? If the number, and I subtract by 1 every time, right? I do 4, 3, 2, 1, 0. By the time I hit 0, I want to stop, right? That's my base case. I just want to return because I cannot call the factorial function anymore. So how could we translate this into code, right? If I know that my base case is 0 and that's what I want to return, I can say something like if n is equal to 0, return 1, right? This is it. This is when I reach my base case and I want to return 1. When n is equal to 0, which is the number that I get. And here comes the magical part, recursive case, right? Like something that we keep doing over and over and over again until we indeed reach that base case. So I'm going to say else. I want to have this recursive case. And what would my recursive case be? How can I write my recursive case here? What is this recursive case indeed? Exactly. So whatever number I have times factorial function of n minus 1, right? I always want to subtract by 1 before I pass in that number to the factorial function. And I do want to return it, right? So as we saw just now on the slides, once I reach my base case, I start returning those values back up again. So I want to make sure I also specify that in my code, okay? So once again, our base case is 0. This is where our program will stop and sort of like collapse all of this again. And the recursive case is this like magical step where the computer just figures out by itself what it needs to do. Okay. So let's try compiling it. I'm going to run factorial number 4, and I indeed get factorial of 4 is 24. Okay, and then let's try factorial of 5, that's 120, right? So it recursively calls sort of like function on itself, and you can always imagine it sort of like expanding it until it reaches that base case, and then every time it returns its output, it collapses itself back up again. All right. Any questions about recursion or this exercise of factorial that we just did? Yeah, so someone said, could we do n equals 1 or equals 0? So technically 1 could work here as well, because the factorial of 1 is 1 as well, but 0 would be our base case here, because the factorial of 0 we can calculate, and it is in fact 1. What is the difference between recursion and looping? That's a very great question. So it's sort of the same, right? Okay, let me backtrack here. Recursion and loops can use in similar ways, but slightly different, right? And a lot of the times, loops just take a lot of space, right? A lot more functionalities to write out. And if you know this recursive step that you can take in the base case that can stop it, recursion can often be quicker, right? Because we just saw that it calculated factorial just like that, and loops can just take a little bit more time. But especially in this class, recursive solutions and solutions using loops can be interchangeable. Okay. All right, so let's go back and let me just click through these guys real quick. But thank you so much for joining. Oh no, okay, wait, let me stop here. I'm gonna restart. Okay, this was week 3. All right, thank you so much for joining us today. This was CS50 week 3 on algorithms. I hope you learned a little something about searching, sorting, struct, and recursion. We will be in this spot again next week to talk about memory. Thanks again for joining and hope to see you soon.